So in this area of two isotropic point sources here, we are having five cases here, which we have to understand clearly here. If you understand the first case here, it is very easy for us to proceed with the second case, third case, and fourth and fifth case here. First case is we are having two isotropic point sources here, which are having the same amplitude and the same phase here. Okay. The second case is the same two isotropic point sources of same amplitude but opposite in phase here. Two isotropic point sources of same amplitude and in phase quadrature you can consider. And the fourth case is two isotropic point sources are there of equal amplitude and any phase difference we can consider. Two isotropic point sources of unequal amplitude, any phase difference is the fifth case here. So there are five cases are there here, which we are going to discuss here. So let us begin with the first case here. If at all we are clearly able to understand, and that will be very sufficient for us to further familiarize with the second, third, and fourth thing. So let us understand the first case here: two isotropic point sources of same amplitude and a phase here. So let us consider two isotropic point sources having equal amplitude and the same phase here. So this is the figure here. You can see in this particular figure, we are having the point source 1 and point source 2 here, point source 1 and point source 2 here, which are separated by a distance small d here, small d, which are separated by a distance small d. From the origin it is d by 2, and from this origin is d by 2 here. Both are located symmetrically with respect to the origin here. Symmetrically with respect to origin means equal distance from the origin. So that's why d by 2, d by 2 here. Okay. And now whatever the phi is nothing but here angle here, which is measured from the counterclockwise. Counterclockwise means like this here. Clockwise is like this here. Clockwise is moving towards the right direction, and counterclockwise is nothing but moving towards the left direction here. So phi angle is measured from the positive x-axis here. So, and one more thing is the origin is there. No? This will be taken as the reference for the phase here. Okay, origin will be taken as the reference for the phase here. Okay. So we are going to calculate the field at a far distance here. The near field will always be ignored here. Far field will be considered here when we wanted to describe the sources here. I think I have discussed this point here. When we wanted to describe the source here, we need to describe the source in terms of the far field here, not in terms of the near field here. Okay. So what is exactly the field that is being generated by the point source 1, and what is exactly the field that is being generated by the point source 2 here? Okay. So the field from source 1 at a distance point here, at a distance point in the direction phi is retarded, means is retarded by what it is 1 by 2 dr cos phi here. Okay. So it is been retarded by 1 by 2 d dr cos phi here. Okay. What about the point source 2 here, which has been advanced here? Okay. So we have to consider the reference as the origin here. That's why if you consider the reference as the origin here, at the far field we are going to calculate the strength of the source here. So if you consider the origin as a reference, means it has been retarded here. If at all consider source number 2, it is advanced here. This is retarded and this is advanced here, considering the origin as the reference here. Okay. So what is it? 1 by 2 dr cos phi here. Now what about the dr? Dr is nothing but here distance between the sources here, which are expressed in terms of radians here. We have d, this is d here, right? Small d, distance between the sources here. So this is expressed in terms of the radians here. That is nothing but here dr is equal to 2 pi by lambda into small d here. That could also be written with the beta here, beta into d here, which has been expressed in terms of radians here. Now, what is exactly the total field at a large distance r here in the direction of phi here? Okay, how much is the total field? The two sources are there here. Each source is generating its own field here. So, what is exactly the total field that is being generated by these two sources here at a far distance r here with the angle phi here? What is that one here? So So if at all we look into E is equal to E naught, E raised to minus J psi divided by 2 plus E naught, E raised to plus J psi by 2. Now see, E naught is nothing but here amplitude here, okay? So E naught is nothing but an amplitude of the field components at the distance r is given by E naught here, okay? What is the psi? Psi is nothing but here, it's a phase difference here, okay? So dr cos phi here, okay. So because minus is because if it is retarded here, plus is because it is advanced here. So that's why E is equal to E naught E raised to minus j psi by 2 plus E naught E raised to plus j psi by 2. This is equation number 1 here, total field here, okay, of the two sources here. This is from the source 1 here and this is from the source 2 here. Okay, the first term in the equation 1 is the component of the field due to source 1 here. The second component is nothing but here, it is a component from the source 2 here. So just adding and multiplying by 2 here, what we get here? So you know this value E raised to plus j psi by 2 plus E raised to minus j psi by 2 divided by 2 is nothing but here cos psi by 2 here. Okay. So as the plus term is there, if the same term is minus here, you can have a sin psi by 2. So that's why we have 2 E naught is equal to, sorry, 2 E naught into cos psi by 2. What is psi here? You know the value of psi. Psi is nothing but here dr cos phi here. So dr, you can substitute here. Dr cos phi is nothing but here dr by 2 cos phi here. So 2 E naught cos dr by 2 cos phi here. So we, if at all we wanted to have a normalized equation here, so let us put this magnitude 2 E naught is equal to 1 here and dr is equal to pi you can put, and distance we can consider as lambda by 2 here. Minimum distance we have to consider is lambda by 2. If at all we substitute all these things in equation number 3 here, okay, so we'll have E is equal to cos of pi by 2 cos phi here. So this is the final equation considered with the two isotropic point sources of same amplitude and same phase here. This is the equation number 4 here. Okay, if at all in this particular equation itself only, not in this particular equation here, if at all we consider that two isotropic point source of same amplitude and opposite in phase here. If at all I consider same amplitude and opposite in phase, same amplitude and but opposite in phase here. So you can see here that again the diagram will remain same as it is now. That is point source 1 and point source 2 here, which are symmetrically located from the origin here. That is equal distance from the origin, and the distance between the two sources is kept as small d here. Distance from the origin to source 1 and the origin to source 2 is d by 2 here. But, we need to find the total field that is being generated by these two point sources at a far distance here. We need to consider far field here. Near field is not considered, and angle is measured, phi is measured in the counterclockwise here. Okay, so now what is exactly the field here? As we have described again here, it has been retarded and this has been advanced here. Source 2 is advanced, source 1 is retarded here. So in the same way we are having this particular source 1 is having E naught has a E naught has a amplitude here, e raised to minus j psi by 2. It has been retarded just for minus here, and also it has been again opposite in phase, so that's why minus here. Okay, again the source 2 will be having the same thing, E naught e raised to plus j psi by 2, same thing here. So if at all we consider this one here, taking common E naught as a common, and we'll have a minus sign here, divided by 2 into 2 we have sin psi by 2. Just now we have discussed in the previous case one here. So that's why we're having the 2j E naught sin psi by 2. Okay, so what is psi? Psi, you know the value dr cos phi. Substitute the dr cos phi here. So now what is operator? What is exactly the J indicates here is that it is a phase reversal here. One of the sources out of phase you can consider here. That's why it has been represented with the J here. Indicating the phase reversal of one of the sources results in a 90-degree phase shift here of the total field. Now, if at all I wanted to have the normalization process again here, you need to put the magnitude term is equal to 1. Okay, and the distance between the two sources we can consider as a lambda by 2 here. Okay, so if I consider that same thing here, I'm going to get to the equation as E is equal to sine of pi by 2 cos phi here. The previous case what we got, E is equal to cos here, cos pi by 2 cos phi. Here E is equal to cos sine pi by 2 cos phi here. Suppose if you wanted to find the maximum direction of this particular electric field here, Okay, that is being generated by the 2 point sources of equal amplitude but opposite in phase here. So what you have to do, pi by 2 cos phi m is equal to plus or minus 2k plus 1 divided pi by 2 here. You can write like this. So if at all we substitute the value of k is equal to 0, 1, 2, 3, you will get cos phi m is equal to plus or minus 1 here. As we are having cos value as a maximum is 1 here. When this will be 1 here, either it is a 0 or 180°, then only it is plus 1 or minus 1 here. If at all we wanted to have a null direction, say null direction means where there is no radiations will be there. Okay, so we need to find the angle where there is no radiations are there here. So that's how pi by 2 cos phi naught is equal to plus or minus k pi. You can put this one here. So putting the values of 0, 1, 2, 3 with this capital K here, you will get phi is equal to plus or minus 60. That is nothing but here at this particular angle 60°. Okay, point sources of equal amplitude and opposite phase will be equal to 0 here. And again, if at all we wanted half power directions here, again pi by 4 instead of pi by 2 here. Here we had taken pi by 2, instead of pi by 2 we take just pi by 4 here. You will get certain angle here. Okay, so at this point we will be having the half power directions here. This is case number 2 here. Let us move on to the case number 3 here. What is the case number 3 says? It is also same amplitude only, two isotropic point sources of same amplitude but in phase quadrature he is saying here. In phase quadrature he is saying. So that is nothing but here you can consider pi by 4 here. Quadrature pi by 4. So what difference we are going to get here is, if you observe this particular figure here, it is also same thing again. The point source 1, point source 2 separated by distance d here, symmetrically from the origin here. You can locate it symmetrically from the origin, that is equidistance here, d by 2, d by 2. The phi is counterclockwise here, measured here, and we are trying to get the electric field was for these 2 point sources, okay, which are equal or having the same amplitude but in phase quadrature here, that is pi by 4. Okay, so that is what we are trying to understand here. So phase reference again is taken from the origin here. Okay, again the lead source 1 will be retarded by 45° and the source 2 will be advanced by 45°. In the previous case we have not mentioned regarding how much it has been retarded or how much it is going to be advanced here, but in particular case we are specifying at pi by 4 it has been retarded and pi by 4 advanced here. So in this case just adding pi by 4 to the first case here we'll get the total field here. Okay, so till then we'll just go here. So total field in the direction phi at a large distance r is given by, you can write the same thing here. Only thing we can change here is pi by 4. Just add the pi by 4 here. So final equation what you're going to get here is again cos of pi by 4 plus pi by 2 cos phi. It is the same equation as of case 1 here. Only change we are having here is pi by 4 addition has been done to this particular final equation, that is the electric field of 2 point sources of same amplitude but in phase quadrature here. And this is how we are going to get the case number 3 here. Okay, case number 4, any phase difference is saying here. Again the same thing, that is 2 isotropic point sources are there here of equal amplitude only but any phase difference they are saying here. Any phase difference means this whatever the total phase difference was there, no, total phase difference psi is equal to we have written in the first case, no, psi is equal to dr cos phi plus delta will come here, delta will come here. So total electric field at a distance point is given by again the same thing here, that is point source is going, one is going to generate certain radiations here or electric field, point 2 is also going to generate certain radiations here. Okay, we are going to calculate the electric field at a far distance r here and considering the angle counterclockwise here. Okay, counterclockwise. So what is the total electric field is the thing, but here again E is equal to E naught e raised to j psi by 2. Again the same thing will be there here. Any phase difference he is saying retarded minus says that. Okay, so again we'll get the same thing 2 E naught cos psi by 2 here. For the normalization process here, if at all we consider 2 E naught is equal to 1, then E is equal to cos psi by 2 here. So in this case what we're having here, the addition of the delta by 2 here. Okay, so if you look into, if you compare this equation with the first case here, E is equal to cos of pi by 2 cos phi is there here, right? this much only is there here. Now just addition of delta by 2 will be there, the fourth case here. Any phase difference with delta by 4. In the case number 3, it is quadrature is there, so that is plus pi by 4 here. Okay. Now, case number 5, last one here. Two isotropic point sources are there here of unequal amplitude here. There. We are having unequal amplitude here of the two sources, and also any phase difference you can consider here in this case. Okay, all the 4 cases are having the equal amplitude. There is change in the phases only we're considering here. Same phase, out of phase, and 45-degree. That is nothing but quadrature here, or any phase here difference we consider. Last case is unequal amplitude and any phase difference here. This is the most general case one here, again involving the two isotropic point sources where the amplitude are unequal and any phase difference is there here. Again, we are going to here a little bit of change in the diagram will be there here. So source 1 will be located at the origin here and has the larger amplitude of E naught at a far distance. Large distance R here, and source 2 is located at a distance D, and which is also having the amplitude as a E naught here. Okay, so again the phi is been measured as a counterclockwise here. So the magnitude and the phase of the total field E is given by, we can consider here as a E naught into bracket of 1 plus of A cos psi whole square plus A square sine square psi. Angle could be written as arc tan theta, that is A sine phi divided by 1 plus A cos psi here. So psi is nothing but here dr cos phi plus delta here. So here we can, this is a total electric field. It has been given here from the point source 1, which is at the origin 1, and the source 2, which is the distance t here. Okay, so now if at all at a far distance point P, what is exactly the electric field? Both will be generating a different electric field, E1 plus E2. The magnitude, or what you can say, that amplitude is different here. That's why E1 and E2 is there here. Okay, any phase you can say E is equal to J, as it is kept at the origin here. So there will be, origin will be the reference for the phase here. So phase will be 0 here. So that's why there is no phase component here. So here we'll be having certain phase component with reference to the origin here, with reference to the origin. So that's why there will be certain phase here. That's why we are having total phase difference as psi here. So we can take even as a common here. So K is equal to E2 by E1 here. So total electric field at a far distance, we could write it as E is equal to E1 into bracket of 1 plus K into E raised to J psi here. Okay, this much we can write regarding the case phi here. So this is unequal amplitude and any phase difference here. That's what the equation is there here. So in this, the only change we can find in the case number 5 here, where the diagram itself is a little bit different here. That is, one source will be taken at the origin and another source will be taken at the certain distance D here. Now all other 4 cases here, we are taking what you can say symmetrically located at equidistance here from the origin here. Okay. So this is how we can get to the case number 1, case number 2, case number 3, 4, and 5 here. Usually case number 1, if you understand, no, then it is very easy for us to represent with the case 2, case 3, case 4, and further case 5 here. So case 1, if you know, it is very easy to represent with the case 3 and case 4. It just add pi by 4 and a delta by 2, that is quadrature and any phase difference. In case 2, what we're going to get here is instead of cos value, cos, you will get the sine component here. The last one, we are having two isotropic point source of unequal amplitude and any phase difference. We are going to get some unequal amplitude. E1 and E2 we need to consider here. So even source is that, I mean point 1 source, which is at the origin, so there is no phase difference here, and hence we will be having 0 phase difference at the E1, that is point source 1, and point 2 will be having certain phase difference here. Okay, from the origin here. So this is how we are going to understand regarding the 2 isotropic point sources of same amplitude, uh, same phase, opposite phase, quadrature phase, any phase, unequal amplitude, and any phase difference. Okay, okay, thank you.